Great, welcome everyone. It's really a great pleasure to introduce Professor Ceder here. Gerd is actually a long-time colleague and friend, almost at the same time. But he first got his PhD at UC Berkeley with Didier Desfontaines, working on alloy theory, and he moved right away to a faculty position at MIT in 1991, rising through the ranks. And he stayed at MIT, I think, around 2014, 2015, after which he moved back to UC Berkeley, where he's the Samson Distinguished Professor and also a senior scientist at Lawrence Berkeley Laboratory. Many very prestigious awards. Some of them are the Gold Medal from the Material Research Society, the MRS Theory Award, or the Humrothery Award from the TMS. Is a member of the National Academy of Engineering, a member of the American Academy of Arts and Science, created many startup and successful companies. I think one of the forces behind the original materials genome initiative, and also about materials design and discovery. And I think today we'll learn more about what the future is going to bring. They're very much welcome.
Thanks, Nicola. Thank you for the introduction. I think I was here, it was 10 years ago or something like that, when the Materials Genome Initiative was kind of new and we were all into high throughput computing. So today is going to be a little more about what we think is the next stage, but we can certainly have some debate about that. So I want to acknowledge my funding. This is one of these projects that we never truly had money for, so we leveraged it out of a lot of different projects, and today that's still kind of the case. So to go back to what Nicola brought up, which is if you read the first white paper of the Materials Genome Initiative, this was probably published like 2011 or so, 2010, 2011. There is this graph in it sort of that tries to explain why materials commercialization and development is so slow, that there are essentially 7 or more stages in commercialization of materials, and all of them require an enormous amount of iteration. So as you move through them from kind of discovery and design through synthesis and improvement and development, there's an enormous amount of cyclic development, and very often this is only handed off once something is done here. And so total time is really simply the number of iterations you have to do times the iteration time. And to make this faster, you can work either on the number of iterations, which I would say is being smarter, right? If the more we know about materials, the less we have to iterate on, or you can work on the iteration time and sort of try to be faster at it. And I think the best is probably to work a little bit on both, as I'll try to point out today. Half of my background has certainly been in modeling, and if you look at the sort of computational tools we have today, there's a long history of, I would say, becoming better and accelerating. Just to walk you through the very quick part of that, because it is really, in my opinion, a nice example how fundamental science leads often to things that you did not expect. Right? In the 1960s, we had the first theorems of density functional theory. I am sure that they had no clue what this was going to lead to, just to be clear, right? If you actually read the paper, there's nothing about practical stuff in there. You know, in the 70s and sort of into the 80s, we had sort of people building kind of the first practical pieces, right? Building pseudopotentials, the local density approximation. And then when my career started, which was basically early 1990s, I was lucky. I call it the era of practical DFT that started to arrive. You know, codes became stable. You didn't have to worry the whole day about your K-point integration algorithm, whether your pseudopotential was right, how to do convergence. So we sort of got in there. It was also the time of GGA. And then the logical consequence to that was taken in sort of the beginning of this century, right, when, well, things became stable, so could we just scale them and do high throughput DFT? Right, so suddenly we went from doing one DFT calculation at a time, writing input files, to doing hundreds and even thousands at a time. that culminated, at least on our side, into building workflows, right? If you had stable calculations, you could now organize them with logical decision points in between them, which is really what a workflow is, that you could do higher level problems than just, I need an energy, or I need forces, or I need a band structure. You could put it together in decision-making algorithms. And then, for us and with Christine Persson, who I think has given a talk here, that led to the materials project. On the functional development, scan arrived. And then something we probably none of us had anticipated is in the 2020s, really this decade, we see an enormous amount of machine learning from high throughput DFT, which certainly wouldn't have been possible with high throughput DFT. And I can certainly tell you when we were working on high throughput density functional theory, I think we sort of started in the early 2000s. We didn't even conceive the kind of machine learning you would do today. That was not on our radar screen. And even when the materials project was built, right, and a lot of people have pulled data from the materials project to machine learning, we had no clue that that data was going to be used for machine learning. It was really meant to kind of inform the experimental community at the time. So that's sort of what has happened through modeling, right? Enormous advances. But as I'll show you, obviously modeling can't do everything. And so the experimental tools we have, I think, have taken very different tracks, right? If you look at the innovation on the experimental side, has often been on resolution improvement, right? If you, for example, look at microscopy has undergone dramatic improvements, right? The things you can do today are really amazing. Some new capabilities, but not necessarily on higher speed. I mean, there certainly are examples of it, but not so much on higher throughput and higher speeds. In the 90s, there was certainly a period where combinatorial experimenting, or COMBI as it's named, was very popular. Sort of Rolls was enormously excited. There were startup companies in the COMBI space, but the excitement of that certainly declined quite a bit, and we can have a conversation why that is. And I think the autonomous labs of today have learned from that what not to do. And the autonomous labs of today are probably almost orthogonal to what COMBI was in the 1990s. And I think there's still a big question of how you actually infuse AI into experimental research, into experimental analysis, and how you use it to accelerate it. I certainly don't have all the answers on that. I'll show you a little bit of it, but I think there's a lot of work and ideas left here. So the only other intro slide I want to show you is that when we deal with sort of materials design, and so half of our funding is kind of on the fundamental side, half of it is work with companies, or on the more applied side of the Department of Energy, that we tend to think of a materials design problem as some optimization of some property and something we learn to compute. And maybe it's a transport coefficient, maybe it's thermoelectricity or some property we know how to compute. But the reality is that no real materials problem is solely optimization of a property. It's really the optimization of a property under an enormous amount of constraints. And these constraints are sometimes properties you can easily imagine. Sometimes they are sort of vague, like, scalability, synthesizability, sort of economic viability can be very vague. And many of these properties we can't actually calculate, even the ones that are well defined. And so if we could do that, right, then we have a purely mathematical problem, and we wouldn't really need a whole lot of experimental iteration. If I could turn this into a pure math problem, I have to optimize something, and I have to, deal with the corrosion resistance and with the synthesizability and with whatever else, then I have a math problem done. But we are quite far away from that today. And that's why I think we need this strong synergy with experiments, except that as computations have gotten faster and better, we're sort of becoming gated by the slow speed by which we can do experimental input. And that's going to lead me to what we call A-Lab, but A-Lab was really conceived as a problem we had with synthesis. So we were early on in discovery of novel compounds, especially when we get into high throughput computing. We got all these other interesting compounds come out with interesting properties, and we couldn't make them, or it took forever to make them. There's now many more databases, right? There's the Materials Project. Google DeepMind came out with a data set. Alexandria has a large data set. But I'll give you a few failures here of examples that we still fail in today. This material here, sodium molybdenum fluorophosphate, there's a real interest in sodium batteries. This is actually the perfect sodium ion cathode. It has the best voltage. It has a perfect voltage, high capacity. It's actually, if you're familiar with the terminology, energy on the hull, it's actually on the convex hull. Nobody's ever made it, never. And we have tried. Another one here, this molybdenum oxyphosphate. This is actually above the hull, but not dramatically. This is the fastest known, or I say predicted, magnesium ion conductor. Nobody's ever made it. Okay. So we have a lot of these cases where we have interesting materials. And, when you actually try to make something, the problem is you send a student or a postdoc into the lab and they try and it doesn't work, and they try and it doesn't work, and you never know when to quit. Because there is no theory of synthesizability, right? There is no, did you just not try hard enough, or, or do you need to hire a better student? I don't know. Okay, so we know a little bit through the years, and the theory of solid state synthesis, so we're really in inorganic chemistry here, is rapidly improving, and that's maybe a topic for another time. I think the next decade, you're really going to see good theory for inorganic synthesis. You can see the nucleus, no pun intended, sort of that theory building already. But a few things we know. So theorists use this concept of energy above the hull, which, if you're not familiar with, it's essentially energy above the ground state line, or the set of ground states, as some metric for synthesizability. So a few years ago, when Hassan and I asked the question, how good is that? Or how predictive is that? So what we did is we took all experimentally known compounds in the ICSD database, so all things that were synthesized. This is actually not all. We left the metals out. We grouped them by anion chemistry. And we looked in the materials project, and we looked at their energy above hull. And so what you find is that, so this is the range sort of in which you find them. I think this is up to sort of 90th percentile, that a lot of them are sort of in the range between 0 and 100 millielectron volt per atom, or so 10 kilojoules per mole. Nitrites are an interesting exception. So nitrites have much higher metastability, right? And they really stand out. And you can explain that probably because of the extreme high stability of the nitrogen dimer, right, which is a triple bond. There's a paper that followed up on this from Christine Pearson's group, where they more finely organized this by chemistry, which is really an interesting paper as well. So you see this, and you're a theorist, and you go like, perfect. We cut off at 10 kilojoules per mole, everything below it we can make. Well, turns out that's not true. Because if you do the corollary to that, you now ask the question, like, can I make up things that are in this range, and can they be made? The answer is actually no. And here's the data that shows that. So in this sort of computational experiment, we decided we would take some really well-known chemistries, like zinc oxide, TiO2. So TiO2, there are 15,000 papers or something like that on TiO2, right? So many people have tried many different synthesis routes to TiO2. So what this shows is the energy, and in blue is the phases that have been reported for TiO2. In red is things we made up. So we made different crystal structures, different phases of TiO2, and we calculate their energy, and we did that the same for all the other ones. So what you see is, while all the known phases are all in this 100 MeV range almost exclusively, there are also a lot of phases there that we have never seen before. And you could argue maybe TiO2 has all these unstable polymorphs, all these metastable polymorphs, but I would argue people probably would have seen them, right? Because there are like literally 15,000 papers on TiO2, same with zinc oxide. So the conclusion of that is that lowish energy, if you could call it, seems to be a requirement for synthesizability, but by no means a sufficient condition. Okay. So that's kind of when we sort of conceived ALAB, that we said, well, we just have to get faster at doing synthesis, just to do the experiments faster, but also to create data sets from which we can learn, and that led to ALAB. Sorry. So the objective of ALAB, which is an autonomous solid-state synthesis lab, because we had to leverage out of many different funding sources, there were a bit of requirements that we sort of imposed upon ourselves. First one was unrelated to funding, but we wanted to build something that wasn't just an autonomous lab, but could integrate as much knowledge and data as available. So this was something that had to be able to communicate with things like materials project to put thermochemical data. We tried to infuse it with literature data. There were decision-making algorithms on the side. So it had to not just be a synthesis lab with robots, it had to have a lot of software and data on the side from which it could learn. A practical thing, it had to be able to work with powder precursors. That was because we wanted to remain close to industry processes. We wanted diversity of precursors possible. Handling powders is a lot more difficult than handling liquids. So in labs autonomous labs where people use liquids, there's a lot of valves and pumps and stuff like that. It's usually much smaller scale. Powders is weighing things, mixing things, and so it's a lot more challenging, but it's closer to, especially in the inorganic field, to industry processes. And this was a hard one. We wanted to make multi-gram quantities. Again, a lot of labs will make milligram quantities to do proof of concept. We wanted to make multi-gram quantities because you could do high quality characterization, but also the real objective, which we haven't realized, is we are building a performance testing lab behind us. So we make batteries with it, we make solid state conductors. And for that, you need multi-gram quantities. Obviously, you want it to be flexible and extendable, handle unpredictable outcomes. I'll show you is a major issue. If you go to autonomous labs or autonomous setups in industry, they are usually designed to do the same thing over and over again with extremely minor variations. If you do research, that's the last thing you do, right? Things change all the time, and I'll show you some of that. It had to be organizable into workflows, which goes together with the flexible and extendable. And this is similar to what we wanted to do, similar to what you do in computations, where you may have codes that give you energy, things that give you thermal properties, and you want to organize them into workflows so that you can do decision making. So it had to be not an assembly line type of automation. And it had to have at least a low level of decision making so that you could do self-iteration in the lab without human intervention. And that was more for funding. It had to be able to work like a computer queue where you could send multiple jobs interdispersed, because we were like getting all this money from different projects. So this thing, as I'll show you, runs like a queue, really like a computer queue. You queue up a lot of jobs. There's a scheduler that figures out in what order to run them. And they could be from 5 different research projects at any given time. And of course, you log and store all the data. Okay, so here's what the elements of A Lab is. There's a compute element. A lot of that is actually still outside of A Lab. We pull data from materials project. We have been working on trying to do that on the fly, like do simulations on the fly, but haven't fully integrated that yet. Today, it's more like data that's already generated. So there's a synthesis engine, which makes the material. There's analysis, and there's decision-making, right? Decision-making basically means that you didn't get what you wanted. What do you do now? And so the input is, in our case, the data from the materials project that we can pull on at any given time in the process. We have a large data set that we text mine from the literature on synthesis. There's a lot of machine learning on the analysis, and this is the piece that's certainly undergoing a lot of changes and I would say every few months. And that there's sort of an infusion of science, of synthesis science, which is also rapidly evolving. Okay, so let me first briefly talk about the data sets. That this is mostly what is used in A Lab to start synthetic protocol. And this is an old idea I had, and I think it's a nice example of how you have an idea that seemed really promising and came out and was okay, but not as promising as I thought. Almost 10 years ago, we thought that we could text mine synthesis reactions. So this is inorganic synthesis from the literature and learn from them. So the whole idea of machine learning. And when we started this, GPT didn't even exist. So this was pre-GPT. And so we did that. We actually made arrangements with almost all scientific publishers. You cannot get these anymore today. They were so naive at the time that we got access to all their HTML files. Don't tell them this. We still have a server with 10 million research papers. Maybe I should have destroyed them. I don't know. And we filtered them on materials content. And then we had all kinds of algorithms that detected whether there were synthesis reactions mentioned. We focused early on only solid state. And since then, we've done solid state and solution-based synthesis as well. So what we did from that, we extracted data sets, and these are published, these are open source now, and they've actually been used quite a bit, especially the solid state synthesis data set. And it's essentially, again, this is pre-GPT, it's a dedicated pipeline of essentially a bunch of convolutional neural networks that were dedicated to things like, you have a paper with 10 pages, where's the synthesis described, first of all, like paragraph extraction. But the hardest part, of course, is what I call codifying recipes. This is taking text and turning it into an algorithmic recipe, which is harder than you think, because people write in the weirdest way, and there's no template. What people specify is not always the same. Sometimes people leave things out. Most language models can easily get confused. I'll give you an example. The example's not here. But for example, if you read this, right, and imagine reading this as a computer, you need to figure out that this is the target of your synthesis, that this is the chemicals from which you start, that these are operations, but that ethyl alcohol, for example, is not a reagent, it's a medium in which you do things, right? It will often get confused if you say, I ball mill this with zirconia balls. Like, it has to understand that zirconia is not a reagent. So you can't just say, I'm going to read all the chemicals and put it together. So there's a lot of sort of fine tuning. And actually our experience today, even with GPT-4, you cannot get it right all the time, which is what you need to do for large data sets. So what is this good for? So we got this giant data set, and I'll tell you, I thought I'm going to learn the magic of synthesis. I'm going to now come up with a new compound, and I'm going to sort of machine learn how to do this from all this data. Well, I'm going to first tell you what works, but most of all, it was a big disappointment because we probably could have known that there was not enough data in the literature, but I'll show you some things that did work. So a precursor recommendation is the one that works really well. And so what we do is essentially we train a model in the same way that you train LLMs now by masking data, right? So you have something you're trying to make, a target, you have a set of precursors by which that made in the literature, and you train the model to learn to give you the precursors by masking the precursors and making a prediction and doing back propagation to get that right. So that it has learned very well. So if you give it now a new compound, or in this case, that it's essentially a cross-validation type experiment, right? Where you take synthesis reactions for which precursors are known. If you give it a number of attempts to come up with the right precursors, machine learned does much better in terms of its success rate than what I would call naive guess. And naive guess is a little hard to define. We took something like, I take the most common things we have on the shelf, right? As a naive guess. So I would say clearly it understands some chemistry here. I would say my first and second year graduate students kind of learned this. But so you could say we got sort of this very basic level here, but not more. When we tried to do more complicated predictions, we found that there was essentially not enough information there. Like temperature is an interesting one. The temperature of a solid state synthesis reaction. If you look at observed versus predicted temperature, there's a lot of scatter. This is also a complicated prediction because when somebody says I do this reaction at 800 degrees Celsius, that doesn't mean it doesn't work at 790, right? So temperature is essentially a distribution. And so it's a little hard to define what accuracy means. But some interesting things you learn, and this was the most interesting, what we looked at is how the chemistry influences the solid state synthesis temperature. And the elements in blue are the ones that lower it from some average, and the ones in red are the ones that increase it. So you have some guidance here about where to start. And you could kind of figure this out from your chemical knowledge, like say lithium and sodium lower the synthesis temperature, typically because they're volatile, right? Their oxides are volatile. And then you got these refractories like tantalum tends to raise the temperature, right? Because it's an extremely high melting point system, it's oxide. So some of it makes sense. Boron typically tends to require high reaction temperatures as well, boron oxide. So some of it makes sense, but otherwise, but what we still could not predict is whether something was synthesizable or not. So the sort of question to start with, and the reason is that almost all experiments in the literature are positives. So almost everything in the literature is positives. And the negatives are, if they're in there at all in the paper, they're kind of hidden, like in some statement that's usually not described in synthesis, where, oh, we tried, and this is the best case scenario, we tried this and this, and it didn't really work, and it's usually given without any detail. So because you have only positives, you really can't predict synthesizability. Not clear that you could do it if you had negatives, but certainly we didn't stand a chance. So that's why we built our own synthesis engine, and that's what became A-Lab. And so I'll walk you quickly through the hardware and then just some of the challenges. And this is certainly the lighter part of the talk. And then at the end, I'll show you how we slowly have started to build workflows, just like in computational engines. So again, A-Lab is a lab for autonomous solid state synthesis. Is built by a whole team, but the key issues were these three people, Yan Zheng, who's now a professor at Florida State, and Bernardus Rendy and Yuqing Fei, who are still graduate students with me, but who started this on day one when they walked into their PhD. I said, I need you to build an autonomous lab. So it's essentially three major parts in the original setup, and the original setup's been growing. You have to sort of prepare your precursors. So this is dispensing, weighing, mixing them. It's heating them in furnaces. This is all high temperature synthesis. And then retrieving the powder and doing analysis on it, characterization, which in our case was originally XRD and is now more and more becoming XRD and SEM EDS. And this is, of course, where we're adding other things now as well. So let me show you a little bit of detail of them. So this is precursor mixing and loading. So you have a rack with a bunch of precursor. This is all driven by an API. So you queue up, a bunch of synthesis you want to do. There's a scheduler. The scheduler also has to keep in mind what precursor we have available that day. We have a limited set. If I did it again, I would buy a bigger precursor rack. So it weighs powders, which puts them in this slurry mixer, and then this is the evaporation of ethanol because it's mixed in ethanol. This works really well, this stuff like that, but this you could only do in the last decade. So careful dispensing of powders has been a challenge because of electrostatic problems, and these problems are all solved. They were not solved by us, but these are not all solved in the industry. So then you transfer to furnaces. We can do heating in air, in box furnace, or we can do heating in the furnace you see on the bottom, which are tube furnaces, which have controlled environment. You can flow argon, you can flow oxygen or mixtures of hydrogen, reducing mixtures of hydrogen. So robots load. So there's zero human interaction. So I'll show you the whole loop. There are no humans in the loop here. Okay, so after whatever heating treatment you do, and the scheduler may take into account what you saw, like 8 crucibles went together, what temperature regime they want, comes the hardest part, and this was designed by my students, which is you now have to extract material from these crucibles and start to do analysis on it. So this is the powder retrieval and sample preparation. So this robot is making a sample for X-ray diffraction. This is the diffractometer. There's an external loading capability on it. So crucibles come in on the right, and the robot has to turn this into a powder on this diffractometer holder that you see. The powder has to be fine milled, or your diffraction signal is good. There has to be enough powder. So it uses this salt shaker approach, where it literally just dispenses powder. But I'll show, this is the case where it works. I'll show you some of the cases where it's problematic. In this video, I won't see it, but later it actually flattens it, so you have a flat reference plane. Let me just skip this. But I talked about you have to be able to deal with variable outcomes. So again, we don't work on just one chemistry. We work on many different chemistries, exploratory chemistry. So I took here a picture of, like, I don't know, was that 8 or 10 different things as they come out of the furnace. So here's one where the crucible is just empty, everything evaporated. And again, you're in exploratory conditions, you have no idea. So if you don't do anything, you turn this over, there's nothing on the X-ray diffractometer holder. Here, the stuff is really glassy. Right? It's actually not even formed the crystalline phase, and it sort of like sticks everywhere to the crucible. Here's kind of chunky powder that if you were to shake it, it would sort of slowly come loose. What you really want is this. This is the one you want, is just powder. You flip it over, it all comes out. You know, sometimes it's like rock hard crap, It's really like super hard. You don't know what to do with it. And so you have to deal with all these various circumstances. So what do we use? We use a lot of optics, so a lot of optical recognition. So we take images of everything. We do a lot of visual AI to recognize what's going on. And then we try to dispense. We do the cameras, the robots have cameras on them. So we track how well this is the diffractometer hole, it gets filled. And we also weigh constantly. Everything gets weighed all the time. The holders get weighed, the vials with stuff get weighed before you shake them out, after you shake them out. So we at any given time know how much material is transferred. And then we have an apparatus, a home-built apparatus, where we can basically add steel balls and shake the thing really hard to make things crumble. So this allows us to work to almost all conditions that we experience with this thing. So here you'll see, again, the salt shaker. And I think in this video, you'll see the flattening. So the problem is if you have a pile of powder, your reference plane in diffraction is offset for some of the powder. So what you do is you just flatten it, like you just really push something on it. Okay. Again, so one of the nice things that I found about autonomous labs is that it is so easy to store all data, the data that you think is relevant and the data that you didn't even think was going to be relevant later, right? In a lab notebook, we tend to write down what we think is important. And what we found is there's a lot of stuff that we wish we had, and then only later do you find out. So we take videos of everything. There's video of everything. There's pictures of everything. And this has been remarkably important for error tracking, right? When you find, you come, the lab works 24/7. You come back in the morning, there's something with a sample. You can basically just go and look at the video and the pictures and see what went wrong. You also have historical information. If later you decide that, I don't know, the way something sits in a crucible is important, I don't know, is important, you now have that information. One that's, for example, important is sometimes for throughput, we load multiple crucibles in a furnace together. And everybody always asks about cross-contamination. So cross-contamination is rare between the crucibles a bit, but it can happen. And the way we detect that is we store images of the rack. And when, for example, we have splattering, the way you get cross-contamination is almost uniquely by splattering, right? Something starts to lightly boil. Vapor is usually much less effective for cross-contamination. It also gets flushed away. But we store images of the rack, and you simply do image comparison. And when you see new specks, you've had splattering issues, and you can sort of go back in the data and at least sort of mark that as a potential issue. There's infinite amount of error correction on the robots. If you don't do this, you're like done in like 5 minutes. So even though, the lab is run completely by position control. So the operating system knows at any given time where everything is. But even though you think robots put everything always back in the same place, because robots are not as versatile as humans, even when you're off by 1 millimeter or 2, you have issues. So what you'll see, if you ever come and see this in real world, all positioning is relative positioning. So basically what the robot does, right, the robot feels where the rack is, right, because it has haptic interference, and then it resets its positioning from that. And in that way, it can always fairly accurately pick things up. If you don't do that and you work in an absolute coordinate system, you're down in 5 minutes, like things fail constantly. Okay, software is fairly straightforward. This is open source, is available now on GitHub, the ALab OS. You can probably guess some of the requirements. It has to be modular. It's fully configured for user interruptions. And this is, again, because we're a research environment. So you can do checkpointing in the software. If you want to do something to a sample that is not available in ALab, you can basically checkpoint and say, stop there, notify the user. User comes and picks up the sample, does something to it, puts it back in and continues while all the other samples are moving through. Another one that I had not anticipated is, in any research thing, there's lots of updates and software updates, and we would have to always shut down the whole lab to do software updates. So we build digital twins for testing new features. So we have digital twins of all the equipment that allows us to test new features without shutting down the lab, which has been has gotten our uptime much higher. And then this one is important, that the lab retains experience about problems with precursors. Everything goes back into a database. And so whenever somebody sends in a new recipe that they want to execute on, it gets checked against potential problems. Are the precursors safe? Are there issues of volatility we should think about? Because it's an open lab, we don't work with toxic precursors. But I'll tell you a story. So we don't work with smelly precursors either, because our neighbors don't like it in the lab. But once we made something with 2 very benign precursors, but the result was extremely smelly. And so these are simple things, but you can store these. And so the next time somebody wants to do these, they get flagged. And so when all submissions get run through basic testing, and then they can get flagged to human operators who can then let them through or not. Okay. Operating system is relatively straightforward. Every job is a task graph. Tasks are actually operations, right? Synthesis, operation, grinding, mixing, annealing. And then the devices are available. And essentially, when you submit a job, you can either you can give priorities to the job. It's really just like a computer queue. If the job is critical that it gets done in a certain time, you can reserve assets. Otherwise, you just let them come up in it. Sometimes, for example, after you mix, you want to do the synthesis immediately so that the precursor doesn't degrade. So then you reserve furnaces. Otherwise, you can just let it become available whenever. So how has this worked? We've done about 4,000 syntheses so far. Here's our kind of throughput per quarter. Our failure rate, so we call it our exception rate. This is when a robot cannot perform an action that it's expected to do, is between 0.5% and 2%. But the good news is that most of these don't require people to come in the lab. So what happens is, because you have robots available, the students or postdocs can actually fix most of the errors remotely. And I'll show you some examples of that. So very few of these actually require people to actually come in the lab and fix something. And what happens is, after a lot of these errors, if they have appeared multiple times, then they just get integrated in the OS. And then the robots will actually, so the robots then learn from the humans how to fix the error, and they will actually do it automatically. So here's an example. So this is a homemade cap dispenser. The caps are on the bottom. And so this went a little fast. The cap dispenser, because it's homemade, probably, it actually got stuck. Because they're plastic caps, they're very light because they're cheap, they're disposable. And so really, all the robot does is it taps on the top, because it knows the cap, it couldn't get a cap, the cap dispenser, so it taps on the top. So in the beginning, my students would just do this from home. They would get an error message, they just tap, and now they just program it in. So it's a bit like, if those of you are familiar with Custodian in the materials project, it's just like Custodian. You learn most of the errors and you learn how to fix them, so you start putting it in the software. Okay, so I'm going to end with a few examples of A-lab use. I'll go through this quickly. So the earliest project we did was to see how well it could do broad chemistry. So we took about 50-ish target materials that predicted to be stable in the materials project. And we basically gave the A-lab no information whatsoever about these compounds, except their energetics, but there were no synthesis recipes. So the question is, could it, based on the machine learning and on some active learning, figure out what they were? They were a bunch of diverse chemistries and crystal structures. And it was successful about 70% of the time. And I'll go through where the errors come from. 35 out of 41 were actually already successful from the recipes suggested from the machine learning, right? This is, we would give it 5 attempts based on the text-based machine learning. The other 6, it goes into what's called active learning. So actually what it then does, it starts to analyze its failures. It tries to analyze what actually did form instead of the target, and it modifies the precursors on that basis. So going back. Failures were actually kind of interesting, and we've learned a lot from this, so that if we did this experiment again, we would have a much higher success rate. The highest amount of failures is what we call slow kinetics. And really what happens is that your precursors react and they form something that's not the target, but that consumes almost all the free energy. And so what happens is you made a reaction intermediate, and now you have almost no driving force for reaction anymore, and so it just sits there. So typically, if you know this, what you do is like what people in a normal lab do. Either they, raise the temperature, let it sit longer, or they regrind to remix. So sometimes you hear like people take something out of a furnace, regrind so that they remix things, reheat. That was actually a lot of the failures. Other failures, there was one that was amorphous, volatile precursors. And again, this is stuff that you learn with time. So you sort of pick that up, store that, and you don't work with those precursors under those conditions. And then interestingly, 3 were DFT errors. So 3 in some sense aren't really errors because we shouldn't have been able to make them. These are things that are predicted to be on the convex hull, but they shouldn't have been. And the first 2 we're absolutely sure about. The third one is maybe a little more disputable. Like this lanthanum manganese oxide compound is absolutely should not be on the hull because it actually kicks the perovskite, lanthanum manganese O3 of the hull, which is a well-known material. And this is, for those of you not familiar, until a few years ago, there was a pseudo-potential error in the materials project on molybdenum compounds. And so this one was from that period. And so that one has a molybdenum pseudo-potential problem in the materials project. This is fixed now. But so it's kind of interesting that we actually found some DFT errors in the process as well. You can use this to test synthesis theories now that you can do a lot of experiments. A lot of synthesis theories today are still based, I would say, on the energy landscape, because of course it's much more easily available than kinetic information. So it's lots of papers published trying to take a convex hull and things, close to the convex hull and derive from that a synthesis path or synthesizability. Early work that we did had one particular concept that I'll show you how we can test it. And this is one of the earlier synthesis theory, and it's called the delta G max theory. And the concept was that, let's say you put A and B precursors together and you put them together in a 1:2 ratio. So you're trying to make the AB2 compound, this gamma compound, let's say. But the question is, when you're at this interface, what actually forms there first? And the reason we know that that's important is the first phase to form consumes a lot of the reaction energy. So if that one goes in the wrong direction in your system, it's obviously very hard to get to target. So the delta G max theory says that, well, at the interface, you are compositionally unconstrained, right? This interface doesn't really know how much A and B there is. It just sees infinite A and B. So it's not going to make gamma. It's going to make alpha, which has the largest driving force to form. And that's the hypothesis, right? Maybe calling it a theory is an overstatement. And this came out of early work that Will Richards did on understanding interfacial reactions. But it was really Matteo Bianchini, who's now a professor in Germany, who picked this up to try to understand reaction sequencing in solid state chemistry. So now that we have a lab, we can test this into sort of fairly large scale. So we took a bunch of what I would call binary reactions. So they're ternary systems, right? They're typically either lithium or sodium with a transition metal, and then they're an oxide. So they're 2 cations typically in oxygen. And we did all kinds of reactions with them, and we took the thermodynamic information from the materials project. And what we measure is if a system like this, right, the phase with the largest driving force would be this one, right? Because that's the deepest part, even if you're trying to make something else. And what we measure is the distance to the next competitor to see how much of that is a metric. And you expect from nucleation theory that if this free energy difference is very large, then you will overcome all other nucleation issues like difference in surface energies. And so like that was the hypothesis. Okay, here's the data. So this is the systems, chemical systems. This is the difference in driving force between the deepest well in the convex hull and the second one. And then the blue point is when you actually make the delta G max phase, the one with the larger driving force. The red triangles is when you don't make it. And there's an amazing separation here. So when the thermodynamic selectivity, you could think of this, right? is large, and typically the cutoff here is about 60 MeV per atom, you always make, without exception, and this is like 30-something systems, without exception, you make the deepest well at the interface. And again, remember, that's not the target of your synthesis, right? It's the one that's compositionally unconstrained. When you go below 60 MeV per atom, it becomes much more of a mixed bag. Sometimes you make the delta G max phase, but very often you make something else. So there seems to be a separation here where you have full thermodynamic control at the interface to more kinetic control at the interface. And since this paper, there's some interesting work that's gone at LBNL, and there's a paper on the archive by Christine Person's group, where at least on one system, they have shown ways to start do kinetic predictions on what this first phase to form is. And so I think we're kind of in exciting times that we're getting much closer to predicting reaction sequencing in solid state systems. I'm getting very low on time, so I'm going to skip this example and show you the last example on how you can start to build workflows. So what do I mean with a workflow? Workflow is that you sort of sequence operations and have decision-making between them. And so this is an example from the NASACON chemistry. NASACONs are well, so-called polyanion oxides. They typically have an alkali, sodium or lithium. They have a metal, and usually these have a lot of tolerance to different metals. And then they have a polyanion group. Sometimes that's a phosphate, but you can substitute silicates in here or sulfates and even other polyanion groups. You can sort of mix them in certain ratios. So this is part of ESRA, the New Energy Storage Consortium in the United States, which is trying to make novel sodium-ion conductors, because since China made sodium batteries, we're all super excited now, supposedly, about sodium-ion batteries in the United States. And the reason we're trying to make complex compositional chemistries is because of this paper that Yan Zheng did in Science, showing a sort of high entropy effect on conductivity. So what this plot, which is out of that paper, shows is that if you take, for example, this is the sodium nasicons with sodium 1. If you make them just with one metal, you take them either, so you get a sort of relatively poor conductivity. If you mix the four metals, you get a sort of, call it a synergistic effect, that the conductivity of the mixed system is above all of the conductivity of the individual systems. And this holds for lithium nasicons. This is lithium nasicons. The mixed system with four elements has order of magnitude better conductivity than the individual system. And it even holds in the garnets, which is a different structural class, where here we tested, here you can test individual systems to go charge balance. If you test binaries and then you add the binaries to get into a quaternary, you still get higher conductivity. We know why that is. The high entropy comes from site disorder, that in nasicons, like in so many of these open systems, the pathway that the ions have to traverse goes through multiple crystallographic sites. And that means, because they're symmetrically different, these sites have different energy. And the energy difference gets added to the hopping barrier, right? Because the barrier for an ion to hop is a sort of the barrier to squeeze through. Usually it's an oxygen triangle, but then if you have an intermediate high energy site, that sort of gets added. And so that's what is shown here in an ordered system, the energy distribution of two different sites. So if you add a lot of elements, especially if they're different in size, you create distortions, and these site energy distributions start to overlap. And if you have nearby sites where you're the same energy between the two different sites, you're going to have the lowest possible barrier. And if you have enough of that, you can have percolation. So if you have percolation of these near overlaps in the site energy distribution, you will have lower diffusivity. And this is an interesting thing to remember, that transport in disordered materials, transport is not an averaged quantity, right? It's a percolating quantity, right? Whether it's electrons or ions, it doesn't really matter that I have a lot of pathways that are high energy. If I have a percolating one or low energy one, I tend to have good transport, right? So if I can make instead of having all the same activation energies or all the same migration barriers, if I can separate my system into a bunch of low ones and a bunch of high ones, I win, right? Even though the average stays the same. And that's what high entropy does. It essentially broadens your distribution of migration barriers And if there's enough of the low ones, you get percolation, you get a much better conductor. So that's why we're trying to make these sort of high entropy nasicons or nasicons with many compositions. So this is a very early example of how A lab self-iterates. So what we're trying to set up here is a workflow, and we can start to impose some design conditions. So there's a bunch of hard constraints about chemistries we don't want to work with, et cetera, et cetera. But then to pick certain compositions, we want to add cost functions. You could think of these as our constraints, right? So one constraint is obviously I want to have good ionic conductivity. I don't want just a random nasicon. I want to have good ionic conductivity, but I want to be able to make it, and that's what these two are. Accessibility, I'll show you, and it is actually the sort of historical metric, and synthesizability is where we put all data that we generate in our attempts, but they basically together form synthesizability. So really the whole idea is, right, you suggest a composition, you see if you got it. If not, you have to update your synthesis path, which is usually your compositional model. So the question is, how do we get these constraints, right? So in principle, we could calculate ionic conductivity, but remember, we want to do this on the fly, right? We want to have A lab synthesize, make decisions. So we could, if we had more time and more money and people, you could say, I'm going to do on the fly, say, machine learning potential MD simulations to get conductivity. So for now, we haven't done that. We just build machine learned models for all these properties by which we optimize. And they're certainly not exact, right? If they were exact, again, this would be a mathematical problem that you would solve without a single experiment, right? If you had the exact functions here, why would you do an experiment, right? You'd find the minimum, the optimum in that space. So the models we use are machine learned from literature data. So sodium ion conductivity is expressed here as far as sodium content, average radius of the cation, average radius of the anion. Synthesizability is expressed from this weird metric, which I won't even go into, but this is a classic machine learned metric there. So the greenish points are nasicons that have been synthesized. The reddish points are nasicons that have not been synthesized. There's certainly no perfect separation. So that's what we use now as the constraint functions in this space. So now you can let A lab work, right? So you come up with an initial target. You're trying to make something in, say, this Cherney phase diagram, and you do the analysis, and you find that maybe that's not what I got 3 phases. What you have to understand is it's easy to draw this picture, but in reality, it's a lot harder. I may know or may not that I have 3 phases because you have to all learn it from X-ray diffraction. I probably don't even know these compositions very well. This is really hard to know in multi-phase experiments. So you have to operate here under completely sort of fuzzy characterization, right? But so let's say that this is the situation you're in. This is what I wanted to make. Instead, I find these 3 phases. So what I really need to do is start driving my compositions to these endpoints. And I have to do that under these constraints. So you have to sort of find some vector by which you modify your input. And you do that by essentially testing against these constraints, by imputing these constraints. Where do I find higher conductivity, but where do I still have synthesizability? And of course, you have to weigh these different costs, right? So there's some weighting going on that you have to optimize how you put all these cost functions together. But I'll show you an example. So here's our first attempt. We wanted to make this, you could call it high or low entropy, it doesn't really matter, or multi-element. So equal amounts of zirconium, tin, and germanium. So you make that, it's clear that this is not phase pure. This has multiple phases in it. So what the algorithm tries to do, and this is where it gets very fuzzy and is very inaccurate, which is why you need duration. From the lattice parameter, so it has made an nasicon, and from the lattice parameter, it tries to figure out what the composition is. This is extremely inaccurate, right, for refining a composition. And it also tries to identify the impurity phases. So for example, if I actually really had an impurity phase, I'm sorry if it's hard to read that zirconium phosphate, that means I had too much zirconium and I should reduce the zirconium content. So the algorithm works with this sort of uncertain information to try to suggest modification vectors to the input composition. So the second trial, it tried to make this. Higher zirconium, higher tin, lower germanium content. It's still not, it's more phase pure, but it's still not phase pure. So it keeps on iterating on that. And again, if you had exact characterization and exact models, you would either need only one iteration or no iteration at all. So the reason you need iterations is because your information is not exact. You don't know exactly what you made, you only have a guess. In the third attempt, okay, it goes to even higher zirconium content, getting much closer to phase pure, and by the fourth attempt, it's basically phase pure. So what I've shown you here is a workflow that self-iterates, right, in a completely autonomous way towards a phase pure composition in a high dimensional space. So now we know that this phase exists. So you can do this from multiple starting points. This was actually done without including the optimization of conductivity. This was just iterate towards a single phase point. So we have done this, and I think we've run several hundred NASACONs, and we've come up with, I think, 40 pure NASACONs with 2 elements, over 10 with 3, and et cetera, et cetera. So again, this is in the end not rocket science, but you can literally have the lab just run this. And I think this set of experiments was done in something like 14 days or so, right? I'll show you just one piece of data where you do it with optimization of properties. Here I am not allowed to fully disclose the composition yet, but this is actually a material. Now we're putting in a composition model. And that's actually, by the way, why the sodium content is going up a lot, because we kind of know that with higher sodium content, we get higher sodium mobility. And this is one of the faster known sodium ion conductors in this material. It has 2.4 millisiemens. And this is one where it optimized under the constraints of both synthesizability, but also trying to stay in a domain of high ionic conductivity as defined by that basic model, but then the data is actually really measured, right? Okay, so let me just briefly end. I have 2 minutes, right, to go talk about our future plans. And some of them I stressed, I pointed out already, right? So this would be even more powerful if we had a better prediction on the fly. So if we could integrate in line with modeling. And so we're thinking about that. There are a lot of practical issues of what's the time that your modeling needs. Can you reserve computational resources? This is also an issue, right? Like a lot of us work with queues, and you could submit something and it may only need 2 hours to run, but it's 7 days in the queue. So then you can't work with that. The better the characterization of what you have, the better your decision making, right? And with XRD in multi-phase samples is extremely limited. And then we're also broadening the chemistry by doing an air-protected version of ALAB. This is in the making. This will be ready in a couple of months. We're actually doing a full system in nitrogen-filled glove boxes, so we can work with very different chemistries. Everything before was in air. The handling was in air. The synthesis could be in. So this is kind of in unit testing at this point, but we expect to sort of put this together. We've learned a lot from version 1, so this is a lot more compact. And we will actually do diffraction in nitrogen, so you don't have to protect samples. So everything from synthesis, you will queue up an API command, synthesis and characterization will all be done in the same nitrogen-filled glove box, fully autonomously. Okay, the last thing I'll brief is, and this is one of your own postdoc that works with me, Andrea Giunto, who's from EPFL, has done a fabulous job on working on, we want to integrate SEM sample preparation. So we made a device that actually, this is his colleague that has done it, that autonomously makes SEM samples. So basically you have to get powder from the crucible on that stub. And you have to do it better than a human does. A human just pushes it in usually, and powder just sticks on the stub. And what happens is you get too much clumps of powder. This is actually done by electrostatics. So you charge the stub electrostatically, and then you actually don't touch the powder. You electrostatically just, you hold it slightly above, electrostatically attract the powder, and you can control how much you put in by the distance you put, and so you load up stubs. But the really cool stuff is then, so imagine every sample that goes through ALAB will soon be characterized also by composition. And when you do EDS in a scanning mode, right, you now don't just have average compositional information, you have location information. And that is really helpful because this is Andrea Giunto's work. He has learned to do quantitative EDS on powders, which is non-trivial, right? EDS on powders is really challenging because of the very different angles that radiation comes out. So if you imagine that you do 100 compositional analysis on your sample, you can start plotting the points you get in a compositional space, and you start to see clusters. And this is really powerful because that basically tells you which phases are present. right? And the composition. So in this case, you see that there's a chromium oxide present, Cr2O3, and manganese oxides. And so what the scanning EDS will tell you much better than the XRD is like what your compositional clusters are, and so how many phases you actually have to look for in the XRD. Anyway, so I'll end with that. I'll make a strong statement. I have zero doubt that science is about to change, and I'm not gonna have to deal with it. I'll be retired, but like that, that we are in a time, the way we do science is completely unsustainable, that nobody can read all papers anymore, right? In my field, I'm in 4 or 5 different technology fields, and every field publishes 50 papers a day, like in energy storage. Like solid state batteries, 50 papers a day, sodium ion batteries, something like 40 papers a day, lithium ion is probably 75 papers a day. And that's not even counting the theory work, right, that I should read. So I think that we're gonna have to find other ways to transfer information and knowledge into decision making, right? Because the old scheme whereby I read a lot of papers, I get smarter, and I make the decisions, or in this case, it's gonna be you, right? This is just gonna completely break down, right? The human-centered version of science is unsustainable, right? So what does that mean? That you have to build, we have to get it onto this of learning how to build algorithms that do decision making and interpretation for us, first at a low level and then maybe at a higher level. And the exciting thing about this A lab, I mean, a lot of people see the robots, which is really cool, but the actually exciting thing is the quantification of decision making, right? Because that's what we've been actually really bad at in science. We do fuzzy decision making, right? We look at a spectrum and looks good, looks bad, not so great. And I think that is, in my opinion, going to be the real benefit of autonomous labs, just like theory, right? Theory and modeling led to the quantification of a lot of material science, because suddenly you had numbers. So before theory and modeling, we had very few numbers. And so when you don't have numbers, it's easy to make a theory. Right? If you start actually getting numbers, the energy of this is that, and the band structure of this looks like that, you suddenly cannot get away anymore with making bad theories. And I think that this kind of autonomous lab is going to do the same thing for us. We're going to be forced to quantify how we interpret data. It's not just going to be, let me look at my battery voltage spectrum and see, it looks great. No, not so great, right? We're going to have to actually make decisions about what's going on with them. So we've done that for synthesis. I think there's an enormous amount of work left to do here. So I'll leave it with that, and happy to take questions.
Great. Thanks a lot, Gerd, for this very inspiring talk. We'll take questions both from the physical audience here and from the audience online. So if someone online wants to ask a question, just write it in the question and answers, and either we can give them the audio or I can read the question. So let me see if there are some questions online, but if there are questions from the audience, Manos, and then this.
Hi, Gerd, very nice work. I have a question about the functional properties characterization. And my question is, this is great, I agree with you, the solution to synthesis is to map the synthesis landscape and know exactly how to make something. The question is how to target what to make, right? And I'm asking in particular in the topic where what if the characterization, what if the functional properties emerge only once you have very pure samples, very single crystals, eliminate defects, and it's a very time-consuming process. So what are your thoughts on this?
First of all, I'm a great believer in theory, right? So you can see that A-Lab was conceived with the idea that in many cases you already know what you want to make. So I'm a big believer in theory that, like, we do computational materials design. So it's not like we're randomly exploring space to come up with new phases. That I think a lot of that will come out of computation. Having said that, we are certainly imagining the next loop attached to this, right? You could sort of see that you make materials and now you build a second loop where you test their performance, right? The issue with that is obviously that the more you get into performance, the more you get into application, the more specific the loop becomes. And that you can build, like, maybe you could build 10 labs for synthesis with all kinds of different syntheses, but as you go into applications, there's a lot of different things you have to measure. So we, being an energy storage group, we certainly already have a design for how to make battery cathodes out of this and cell testing. We have a design on how to measure ionic conductivity for superionic conductors, but we just haven't been able to pull the trigger on that, right? So, but I do foresee that I wouldn't see this as a random, and maybe that's the difference with the 90s combi, right? In the 90s, I think the whole idea was, I'm going to do thousands of samples and I'm going to hit on something, right? And I think the perspective has changed. It's more now about, let's try to figure out what it is we need to do and then do targeted attack on that. So it's a bit of a different perspective, I would say.
Thanks. Let's get the microphone.
Thanks. So I have a question a bit more about the sort of software engineering side of this. So when you say that your students program some rule, what do they do in practice? Do they write like a Python script, or what happens?
Well, there's a science side and there's a practical side, right? Yeah, so most of it is all in Python, right? It's Python scripting. That's the practical side. The scientific side is sort of more complicated in the sense that, you know, everybody talks about integrating physical ideas with AI, but it's actually easier said than done, because physical concepts aren't in the same language as AI, right? Like, you know, how do you teach a neural network basic chemistry, right? So I hate to say we don't have a magic bullet. It's sort of on a case by case. Like, I'll give you an example, like the active learning, right? So is what the active learning does is, if you didn't make the target, it tries to identify what you did make, and it backtracks what reactions likely took place. And then it searches through reaction networks to try to prevent those by changing the precursors, right? But that's a sort of specific, dedicated thing to that problem, right? I don't have a solution to this sort of general idea of integrating your physical and chemical knowledge with AI algorithms. Yeah. I mean, some people think you can do that with LLMs, but I think the jury's still out on that, right?
Thanks. We'll try online.
Yeah, if I may, then thank you. Thank you, Nicola. Thank you, Mr. Ceder, for this very, very fascinating talk. This is Eric Macke from Bremen, Germany. I have a rather specific question regarding the details of the synthesis parameters. And that would be, is the cooling rate a parameter which you control and optimize? You know, I'm asking because I suppose that the cooling rate would have a significant impact on the distribution between what you were referring to as thermodynamic versus kinetic outcomes, as you call it, or let's say, in other words, this might provide access to products of high temperature phase spaces, right? The faster you cool, the more you would expect to preserve samples eventually from the high T phase space. Is that something that you factored in?
Yeah, so thank you. It's a great question. So, you know, like in most furnace technology, we can control the cooling rate, but only to some extent, right? So in a lab, we can certainly do programmed cooling, right? And then we can do, I would say, then there's a set of binary decisions you can make. So the cooling rate, the controller is, in some sense, continuously controllable up to a certain limit. But if you want to go fast, which is the one we're usually interested in, right, is, you know, you can only do binary things like open the furnace door, let it cool much faster, take the ceramic rack out, which makes it cool faster. But so there's just a set of binary conditions like that. In the A lab, we don't do true quenching, like quenching in water or quenching on steel plates. And we have a practical problem that our ceramic racks undergo fatigue, thermal fatigue. If we quench them more than 10 times, they break. So that's the practical problem. So in the specific study that I refer to, that you're referring to, I'm trying to remember how they were cooled. I thought they were just air cooled there. I could check that.
Okay, but very, very interesting. Thank you.
So So thank you very much for the presentation. I have just a curiosity. How do you evaluate the minimum energy path for sodium percolation inside these disordered polyanionic frameworks, like from a theoretical point of view?
Yeah. So in that piece of work, right, we only qualitatively explained it that way. So right. So what we did is we calculated the distribution of barriers as a function of a distribution of distortions, right? And we looked at the proximity of them, because you don't just need overlapping distribution, they also need to be spatially overlapping, right? So we did that, but we actually never did a true percolation study. On lithium cathodes, we've done true percolation studies in disorder. And, you do it by building large supercells and either directly calculating the barriers or parameterizing the barrier versus environment, right? And the nice thing is that if you set a threshold for hopping, so that means you decide whether a path is open or closed, then percolation limits are exact, right? They're basically topologically determined, right? So, but of course that requires that you set a cutoff. So you have to make a binary decision. This path is open or closed. Once you do that, it's an exact problem, right? Like there's an exact percolation, which is kind of cool.
Press the button.
Thank you so much for the talk. Go Bears. If you could expand past the dry powder synthesis route, what compounds, what chemistries, what applications would you go? Limitless funding available.
Oh man, I should come to Switzerland. So
let me talk with
yes. We would certainly want to do thin film synthesis, right? Because powder brings us in the realm of a lot of ceramic applications, right? And battery stuff, which is what we are and where most of our money comes from. That's why the first choice was. I think thin film brings you into a completely different realm. And so we actually have some discussions with our colleagues in electronic materials about actually doing that. It's a whole different ball of wax. And so that's certainly one of them. You could add sol gel, but that's not a big expansion from what we do today, right? You do a sol gel. And in retrospect, if I redesigned it, I would probably also still add liquid precursor mixing. Even though it's less versatile, you can do things very rapidly for like test experiments. We are actually, the lab, we are, literally as I speak, we're working on bringing it down. We're rebuilding it completely in a much, much larger space. It's going to look very different in a few months. 2.0 is quite different, and we'll have different synthesis and more characterization in it. It also won't be this handoff. So this is a setup where the robots hand off to each other. So everything is within reach of each other. So it's a topologically very constrained problem, actually. And as you build more, this becomes unsolvable because you don't have enough dimensions, actually. If you would live in dimension 10, then the topology of being near a neighbor is much easier. But that betrays my history as a theorist, that we only have 3 and mostly 2 dimensions. So the new lab is going to be more pod style. So pod style with mobile robot transport between them. So you have stations that do things, and the mobile robot will do workflow between it. So.
Nice.
Thanks very much for the talk. So my question is, how do you balance between flexibility and maybe standardization when you build this kind of A lab? Because on the one hand, like you said, you want to control different equipments, right? But on the other hand, maybe you want to share the recipe, or you want to be able to repeat your experiments. So, for purely software based workflow manager, this is already sometimes contradictory. So I don't know for this kind of.
It's a problem that's not unique to A lab. It's a general problem in science, right? The more you standardize, the less freedom you have, right, to do weird stuff. I don't know. I don't know if I have a great answer that So A lab as it's built today, right, is certainly more limiting than a normal lab. It's faster, it's more efficient, but there's certainly things you can do. right? Sometimes a grad says, oh, I want to do exactly this type of synthesis. Well, sorry, we didn't build it. You can't do it, right? And that's why we do the checkpointing, so that you can take things out. So I think today that's our best effort, that it's not an assembly line lab, right? It's not like if you look at an autonomous lab in industry, it's very much assembly line. I do this, I do that. And so that you can actually either build new stations to do it, or if it's a one-time thing, you just stop the sample, text the person or email the person. The system sends email, your sample is ready, come and pick it up, go and do whatever you need to do. So that's about the maximum amount of flexibility we can build in today. But the problem is, as soon as you get to physical equipment, there's a limit to flexibility, right? Equipment does some things and not other things, right? Like once we decide how we're going to mix our powder, right, the first station, that's certainly a limitation, right? There are other ways to make precursor mixers. And if one becomes important, I could build it, I got to rebuild it, right? But I think the OS is probably the most important piece for flexibility, in my opinion. That you want your OS to deal seamlessly with user ideas, basically, right? If I want to run something twice through the same station or come back to it, you want your OS to have no problem with that, because writing it isn't the problem, right? Just telling the scheduler that you need to do this and then that's not the problem. It's more like that if your layout or your data structure doesn't allow it, then you're in trouble, right?
Thank you so much.
Great. I think I'll get a last question also, because you discussed a lot of this thermodynamic traps. You want to make AB2 and you get a lot of A to B. And so that can very much be one of the problem, but I don't know, one of the problem could be also that your phase is a very narrow space in a phase space. And so there are a lot of, maybe a little bit more higher in energy, but, much easier phases to make or entropically. So I wonder if you have a sense of really what stops you from making things most of the time.
So there are certainly people who've thought in this direction. It's certainly easy to miss phases that have a narrow domain, and you have to define a variable space which that narrow domain is, right? And obviously that can be temperature, but more common it's chemical potential space. That there are certain phases, like VO2 is a good example, right? So VO2 4+ vanadium oxide. Unless you get the oxidation pressure exactly right, you'll make V2O5, the 5+1, or the 3+ vanadium oxide. So there's an example where that's not just about controlling the oxidation pressure in your furnace, it's about locally controlling it in the sample. So there are certainly things that have a narrow chemical potential domain that are therefore much harder to make. In principle, you can get that out of the phase diagram maps, right? I don't think that anybody sort of coded that up yet. Like, how would you deal with them? I'm not even sure we would know how we would do that better control today. And that's certainly something that happens. I think you sometimes just overshoot phases, right? You start with something, you have to compositionally enrich it with something else, and there's some intermediate, just overshoot it, and you never see it. But
I guess you could learn from trying to make always the lowest possible phase, because every time you can't make that, there is no thermodynamic trap, basically.
Yeah. I think we're in the very initial stages of sort of understanding this pathway sequencing. But so we are building a high throughput in situ diffractometer right now, which will be an A lab where we will be able to do probably order 5 to 10 in situ synthesis runs a day. So hopefully we'll learn a lot more.
Cool. So you'll come back.
There you go.
Yes,
Yeah.
unless you move here, of course. Thanks again.